It's probably not a surprise to you that we would like to know or be able to predict whether or not a particular reaction that we might write down will actually take place. It turns out that there are two things primarily that you need to know in order to make that prediction, one of which we've already talked about, which was enthalpy. The second factor, which we will talk about in this chapter, is entropy. And we will also talk about the conditions in terms of temperature and pressure that are necessary for a particular reaction to take place. The first thing we should probably do is just compare the type of information that we get from kinetics versus the type of information that we get from thermodynamics. So kinetics is concerned with how fast a reaction, or the rate of the reaction, and also the steps, the mechanism that the reaction undergoes in order for the reactants to be converted to products. In thermodynamics, we're interested in initial states, that is the state of the reactants, versus the final state, which is the situation with the products, and that's what we're going to be concerned with. A term that will be important for us, and that we'll use quite a bit, is the idea of a spontaneous process. For the moment, we'll just say that a spontaneous process is one that occurs with outside intervention. But we'll look into what that means exactly in more detail as we go along. So in order to start, let's just consider this situation. Let's say that we have a gas, and it's the kind of two bulb setup that we've talked about before. And initially we have all the gas in one side, so that would be over here. We have a valve that separates the gases, and then over here we have an evacuated bulb with a vacuum. So what happens when we open the valve? Well, I think you know that eventually the gases, or the gas, will be evenly distributed throughout both bulbs, and we'll have equivalent pressure. We've already specified, or we can specify, that the temperature will be the same. So the question is, what is it that causes this to take place? This is not really a chemical reaction, it's more of what we would call a process, but still, what is the driving force that causes this to happen? So if we look at all of our various functions that we could talk about, delta H, delta E, Q, and W, it turns out that all of these are zero for the process. There's no change in heat. There's no change in the overall energy. And since there's no change in the heat, there's no Q, and there's nothing that's being pushed against, so there's no work being done. So basically, none of these are factors in the expansion of the gas from the one side to the other. So if none of the previous factors are responsible, what is responsible? So it turns out that this process takes place because there is an increase in entropy, and that's what we're going to talk about and define more carefully. So for any spontaneous reaction, the increase in the entropy of the universe increases. And you may wonder why we're bringing the universe into this, but we'll talk about that a little bit more later. Entropy can just be defined simply as the randomness of a particular system. So, for example, in the previous example, when the particles are spread out in a larger volume, they are more random than when they were all contained in the one side of the one bulb. Another way of saying the same thing is that entropy is a thermodynamic function, just like delta H was a thermodynamic function, but entropy describes the number of possible arrangements that are available to a system in any particular state. And what has been discovered is that nature spontaneously moves to states that have the highest possible probabilities. So let's take a look at a fairly simple system. So this system just consists of four particles, A, B, C, and D. And starting with all of the particles in one bulb, there's only one possibility, that is that all the particles are in this one side. So when we open it, There are 4 ways, so here, that we can have one of the particular particles in one side and all the rest in the other, so that's one possibility. There are 6 ways that we can have an equal distribution, that is, A and B in one side, C and D in the other, etc. And then obviously the ones down here are just kind of the reverse of the ones that we were talking about. So you may say, well, that's not that much greater a probability. I mean, the probability of having this arrangement here, arrangement number 3, is not that much greater than the possibility of having arrangement 2, and that's true. However, when we are dealing with moles of substances, then we don't have only 4 particles. We have Avogadro's number of particles. And when we have that many particles, the difference in the most random distribution and the other distributions is considerably greater. So great that we would be surprised if we had anything other than the most random arrangement of the particular particles. So, if we are comparing just the physical states that a particular substance can be in, and we want to know which one has the greatest entropy, that is, the greatest number of states that the particles can be in, a gas has much higher entropy, that is to say, much higher disorder than a liquid, and a liquid has higher disorder than a solid. So we would say the entropy of a gas, all other factors being equal, is greater than the entropy of a liquid, which is greater than the entropy of a solid. So now that we've defined the idea of entropy as being the amount of disorder, if we look at some different type of events that can take place, we can determine if the entropy is going to be increasing or decreasing. So we refer to that, the symbolic way that we refer to that is we say delta S. So when you have the evaporation of an alcohol, you're going from a liquid, so you're going from a liquid to a gas, so that's an increase in entropy. If you're talking about the freezing of water, you're going from a liquid to a solid, so that's a decrease in entropy. So remember, decrease in the disorder. So water is more organized than a liquid. If you compress a gas at an ideal gas at constant temperature, so you are reducing the volume, so that means that you have less disorder. You have the particles with fewer possible states. So this would be a decrease in entropy. If you heat an ideal gas at constant pressure, then you're going to have more motion, more possible states that the gas can be in, so that would be an increase in entropy. And finally, if you dissolve salt in water, so you're going from, I can write it like this, I can say NaCl solid to sodium ions and chloride ions, so clearly that's more entropy, more disorder when we go from a solid to a solution.